Hi, good evening, everyone, and thanks for joining. I hope my screen is visible now.
Yes.
Okay, very nice. Thank you so much, and I'll just share my screen. So basically, the agenda for today's this session is to revise week 11 and week 12 for all the LLM aspirants. Because what I have come to know from the WhatsApp group that in the week 1 to 4 in the LLM, they are basically the last 4 weeks of this DL. Okay, somebody wants to join. Okay, so I will just quickly go through the motivation for the week 11. So I hope okay, my screen is visible now. My this is visible. Abhi?
Yes, sir. Yes, sir, it is.
Okay. So in the week 11, initially what we were taught that we can have the encoder decoder models for various tasks. Okay, it is like from image to image summarization, image caption, then translation. Lot of things they can be done by the encoder decoders. Where there is an encoder now, the encoder can be this is an encoder. Encoder can be CNN or it can be an RNN. Okay, and then the last vector of the encoder, this is fed into the decoder. This is a decoder. It can be fed as a initial state, hidden state, or it can be fed in the different at all the states also. So is that clear? Okay. Any doubt on this issue? Anyone?
No doubt.
Okay. Okay. Very nice. So from here, the question came that while doing so, uh, professor gave an example of English to Hindi translation or from Hindi to English translation. That मैं घर जा रहा हूँ, and he amplified that when we translate this, so this comes to I am going home. So when we do it naturally, we take some context from the input also. So ma comes from I, ghar comes from home. Now ja raha it comes from going, and whom is am. Okay. So from there, basically the mechanism came that when we have got an output from the decoder, the decoder has got various hidden states. Not at every state, the output which is coming. Now this is depending on particular some inputs of the encoder. So this is H1, H2, H3, H4. So for example, this is I and this is M. So this is depending more here. And Ghar, now the next is M. For example, M will depend on the last one. This is H5. So the concept came that why not have something that at various output states of the decoder, we should have some mechanism by which we know that on this particular outputs or the hidden states of the encoder, we should focus more. So by that, this attention mechanism was formalized, and what it did, so it is the decoder. So decoder, the output will depend now the previous states of the decoder and the present hj. So this is e which is there some function, and this is some function in the decoder. It will depend that what is the previous state of the decoder st minus 1, and this is I'm at this time step, and here I'm coming at hj. So this function can be anything, but we learned that it is v attention into 10 of h u attention into st minus 1 plus w attention into hj. So by this we get this e value. Now there are 5 edges. For example, मैं घर जा रहा हूँ. So there are 5 edges, so we will get 5 e's for this. And when we convert it to the probabilistic distribution using soft maths, so we get the alpha values: alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. Now, at some step, for example, this is for मैं घर जा रहा हूँ. So at and this is I am going home, and I am at this step going. So in going, if we take the alphas, so this will depend on ja raha hu. So here the probabilistic, the alphas, they will look like 0, 0, 0.5, 0.50. So is this clear? How do we calculate alpha and how we are doing the E? Is that clear? Any doubt here in anybody's mind
Yes,
about
clear.
this? Okay, okay, very nice. So from this, Sakya, we are clear about the encoder decoder. Now the encoder decoder can be used in three ways. So I will cover it. Okay, just give me 1 second. I just have a glass of water. Okay, I'm back. So am I still audible?
Yes, you are audible.
Okay, so we have completed the attention mechanism, basically the basic concepts of attention mechanism. So now the encoder decoder, how they can be used? They can be used in three ways. That one is encoder, and we feed the output of encoder to the decoder one way. Second way, that we feed the output of this encoder to all the states of the decoder. This is decoder. So we feed first also, second also, third also. And third way is to use attention mechanism, where at every time step of the decoder, we decide, we come to know that what is the significance of the state of the encoder. Now, here the one of the main limitation is this, that if I have got, for example, H1, H2, H3, H4, H5, and am at some time step ST. So at ST, I can calculate all alphas. Any problem in that? Because my E is depending on ST minus 1, and HJ, ST minus 1 I have got, I have already calculated. HJ, I have got all the values I have got. So all the alphas at this time step, they can be calculated. But can all the alphas can be calculated here? We cannot calculate. This we have calculated. For this alpha we have can calculate, but these alphas we cannot calculate. This is the one of the limitation of the attention mechanism of encoder decoder. Any doubt? In anybody's mind about
No,
this?
sir.
Okay. So from here, what came? The idea of transformer came, and the transformer architecture is entirely different. So I will directly jump upon the transformer, and will cover the transformer steps. This document also I'll share with all of you. It covers all the basics. So I have just rushed through the attention mechanism, considering that all of you have understood. Okay. So now we come to the transformers. Okay. So we have covered that in the encoder decoder model with attention mechanism, alphas can be found at t time step. However, they cannot be found for all time steps at same time. Parallelization cannot happen. Now, what are the main ideas behind transformer model? So, main ideas behind transformer model are that we take this attention mechanism to a different level altogether. What do we do? That we do attention mechanism In the encoder also, okay, till now what we had done between the encoder and decoder. But we know that there was an example of a car and a street and the word it. And in the different context, the it was sometimes referring to the car and sometimes it was referring to the street. So, to bring out the contextual relationships between the words which are there, we can have self attention between all these words. So, that is the self attention of encoder that I will cover how it is done. Then the output vector which we get, this output vector which is there, it is having the contextual relationships or the semantic relationship between these words which are in the encoder, which is for the input. And this becomes an input to the decoder. Similarly, the decoder which is there, now the decoder, how it operates, it has got input, it starts from go, it finds the first word, the first word becomes the input at the this step, it finds the second word, this second word becomes the input at third step. So this how the decoder works. So here also we have got attention mechanism in decoder also, that how these words one by one which are there, how they are related to each other. So that is the self attention part of the decoder. Here we get an output here, like we got one output here. So here we get an output. This output with this again we do an attention here which is known as cross attention. We get an output from here, we pass it to forward feed neural network, then we pass it to linear transformation, and then we come to the softmax function to find this. Now I will cover this in detail how it is done. Okay. So for the encoder part, and please stop me anywhere, anybody gets stuck about this concept or in any concept, please stop me. I will cover it in detail. Any doubt till now in anybody's mind?
No, sir.
Okay. So don't hesitate again because we are transitioning to LLM. So all these fundamentals they should be clear again in our mind. How all these things are happening. So I will. So this is the architecture of encoder decoder, like I covered earlier. This is the encoder. Now this is the decoder. Now I will cover certain differences between the encoder decoder model and the transformer encoder. So in the encoder decoder model, what is happening? We were giving inputs, embeddings. These were the inputs, and now we were finding the hidden state, and this hidden states, then we were passing it to find the alphas and to the different time steps of the decoder. In transformer, what do we do? In transformers encoder, we directly use this inputs. We don't have any weight matrix u. Okay, in the RNN we have got u here and w here. So here in the transformers encoder, these inputs which are there, input embeddings, they are directly used. They are used directly. Okay. And what do we do? For example, I have got a sentence: I am going home. So the word embeddings for I are used. So this becomes H1. M word embeddings, this is H2, this is H3, and this is H4. Along with this, there is something called positional encoding. Positional encoding. Position encoding basically defines that how the words are positioned in this statement. For example, I and home are far away, I and am are close, am and going are close. For this, there is a formula you can go through the slide content. It was not covered in the lecture, but in the last around 10 to 12 slides, this has been covered. And positional encoding for the number of words in a statement, it remains same. For example, I am going home, and I am not studying. The positional encoding for both the statements remain the same, and the input becomes, or the hi becomes, word embedding plus positional encoding. The formula for positional encoding I have included in this document. It is there. It uses the sign. This word embedding which is there, either it can be directly used from like word to back or from globe, or in the transformer some models, this word embedding is also trained, that during the training this word embeddings are also optimized. Is it clear, this part of this, that we can use word embeddings from the word back also, or in some transformer models this word embedding is also trained. It is, these parameters are also optimized, okay, during the training phase. Is that clear, this input part of the encoder? Can somebody say yes or no? Abir?
Yes.
Yes,
Okay,
it is clear.
okay, very good. Now we come to the second part of the this. So we have got now an input. So I will take an example of a word of I am not going home, and we are doing translation. So the H dimension, and every word has got the word embeddings, for example, 512. So we can say this is H1, H2, H3, or we can write for this also H1, H2, H3, H4, H5, and it has got 512 values. 512. Or so we can say that our input which is there, its dimension is 6 into 512 matrix. Now what do we do for the self-attention in the encoder? We have got three weight matrices which are known as WQ, which is for query, WK for key, and WV for value. The dimensions of these weight matrices, dimensions of this depend on the number of heads in the encoder. So for example, if there is only one head, if there is only one head, one head, then the dimension will be 512 into 512. Okay. If there are two heads, then the dimensions will be 256 into 512, and this I will cover later why it is like that. So first let's take a simple example of single head. So in single head what happens, we get q is equal to w into h, wq into h. So w is 512 into 512, and h we multiply by t, for example, or in this, if we are taking 6 into 512, so q is w into h. We will meet the dimensions okay, later. So this also becomes okay, 512 into 6. Similarly, we get k 512 into 6 dimension, and v also 512 into 6. So these are the matrices, but they are having one for each word. They are having one vector. Okay, so there are 512, but for each word they have got like this. Now here, now we find E value. E is equal to softmax of Q transpose into K divided by square root of the dimension of K. Dimension of K, in this case it is 512. This is E is this, sorry, softmax. So this is the E part, which earlier we used to calculate from, and from here we calculate alpha. Alpha is softmax of E, so which becomes Qt k divided by root dk. And earlier, what we used to find context vector in case of encoder decoder. So, like context vector of encoder decoder, here we get S, and S is equal to this softmax alpha into Vt. And once we take the dimensions, they will come the same dimensions as of your H. So this transpose and all that you can check, but finally the output vector S which is there, it is the same which has got. But the beauty about S is what? That it now gets the contextual relations between these words, how the semantic relationships are playing. Is this part clear? How to use Q, K, and V, and how do we get
Yes.
S? Anybody, any doubt in anybody's mind? Okay, so this was for the single head. So single head, what happened? We had input. Now here in the input there were 1, 2, 3, 4, 5 words. So this was 6 into 512. Here we did self attention. Self attention we did. We got S. And S size is also 600 to 500. Now this S we feed it to a forward neural network. How is the forward neural network? This is S. We feed it to one fully connected layer, FC layer. Here is an output layer, same size, and this gets connected. So there are two weight matrices, W1, W2. So basically, it is doing expanding it. For example, size is this 6 into 512, and this is 512 into 1024 or 500 or 1024 into 1. So here we get one bit matrix, and finally we get 6 into 512. So this is the feed forward neural network. This is for a single head mechanism, and the output of this is Z, the same dimension 6 into 512. We have done self attention where we got relationships between the words. We passed it through the feed forward neural network. Again, we got Z 6 into 512, and this is the output of the encoder. Is this clear here for
Yes,
everybody?
clear.
Okay. Thank you, Suresh. Now, what happens in this two head? In two head, the same thing happens. There is an input, but there are two heads. So this is 6 into 512. This is 6 into 512. But here now what will happen that your this weight matrices which are there WQ, WK, and WV, this size will become 256 into 512, and it does self attention. The S1 output dimension will be 6 into 256. Here we do the same self attention. Here we get S2. S2 size is 6 into 256. We the concatenation of these both, we do concatenation, and we get 6 into 512 to get S, and we pass it to forward feed forward neural network, and we get Z. This is clear. And generally in the transformers we use 8 head. So for 8 head, what will be the size of WQ, WK, and WV? The size will become 64 into 512. So we will get S1, S2, S3, S4, S5, S6, S7, S8. All sizes are 6 into 64, 6 into 64. And then we concatenate all of them, and we get a size of 6 into 512. And then we pass it to the feed forward neural network to get Z. Is this clear? Anybody, any doubt in anybody's mind? You can ask me. I can cover it again.
On number of parameters, letter or
Number of parameters, see these weight matrices which are there, they are shared here. So the weight matrix which you are sharing, for example, this is 8 head, for example. So this weight matrix, okay. In here they are shared, but here they are different. So to get different relationships between the all the words, okay. So here WQ, here WQ, they are different. Is that clear?
okay, okay.
Okay, okay,
Yes.
yeah, okay.
Sir, one
So
more thing.
yeah,
Yes, how we are concatenating it? Can you explain that part? Like,
concatenating. Okay, okay. So we know that in NumPy and how do we concatenate? Either we do concatenation vertically or we do
horizontal?
horizontally.
Yeah.
Okay. So we have got, for example, I had okay, 6 words. Okay, H1, H2, H3, H4, H5. From first head, I got this S1 which is there. I got 6 into 64. Okay, for example, 5 into 64. So these 5 values are there, and here I got 64. Is that okay?
Yeah.
S2 I got 5 into 64. So again 64 I get.
Hmm.
S3 I get 64. And now till S8 I get all the 64 and I concatenate. So here I get these values, here I get these values, here I get these values, here I get these values. So concatenation is not addition, it is putting that value with that. So finally, this one was 5 into 64 and it was 8 times. So I get now 5 into 512. Is that okay?
Okay. And sir, one more clarification. Like these S1s are that like after key value query, the thing we are doing. After that, the result is S1, right? For first
Yes,
step.
yes, yes. S is, if I write, S is equal to softmax of Q into K. Just check the transposition and all that. This dimension divided by root dk, the and this total into V dot product. Is that okay?
And yeah, that's good. Like one more thing, like you said the WQ and WK are different for each states, right?
Yes,
Okay, so like so the like yeah, the attention will be different for each state. Okay.
yes, yes. The basic idea for the multi-head is that only, that you
Yeah.
want to find like a different semantic relationships between different words.
Mhm.
Okay, like we used to do in the CNN, we used to have different filters.
Mhm.
So here also we are using different to find like a more semantic relationships. Okay.
Okay. Okay.
Yeah. Okay. Now, anybody, any other doubt? So till now we have covered the encoder. So can we proceed further? Okay, if this concept is clear.
Yes, yes.
Okay. Very nice. Okay. So from encoder part, now I will leave this encoder here as E. We have done. Okay. One more thing before we proceed further. Now this was one multi-head encoder. Now we can have layers also. Okay, and layer does not mean anything. It just means this was one encoder and it was like a multi-headed encoder. And here we got Z values. Now the second layer, this Z value becomes the input. We do everything same and we get another Z1. We do for the third layer, we get Z2. Is that okay? So this remains everything same. The steps remain same. We do self attention, then we do concatenation, then we do forward, feed forward, and we keep on doing in different layers. Is that okay? Layers?
Okay.
Okay. And now we come to the decoder part. So this was total full encoder, different layers and all that. and finally we get from here output, which is Z. And the significance of Z is what? That this not only gets the vectors from the encoder, it also carries the semantic relationships between all the inputs. Plus a positional encoding also, because we have used the positional encoding also. So it carries that information also, that how the words are positioned in the sentence, and along with the relationships between these sentence words in the sentence. Now we come to the decoder. So I will draw the architecture of the decoder and we'll see them one by one, how it is done. So the first part in the decoder, we see it starts with go. We have seen in RNN. So first input is go. It goes, something happens here, I will cover it, something happens here, then is a forward feed forward network, and here is a linear layer, and here we apply softmax and we get the first output, for example. So for example, I am not going home and I am translating it to Hindi. So when the go happens here and this Z is coming at the first step, so first output comes man. Is that okay? And this man becomes the next input for the decoder. Is that okay? This step understood, everyone?
Yes.
Okay. So this is the architecture of the decoder. Here in the decoder also masked self attention happens. I will cover it. What is the meaning of this? Here cross attention happens once you get an output. So here also I will be using the notation, for example, S. Here I will use notation M. Here I will use Z. Here I'll use something, let's call D, and this is output. These are my notations. So at every step, so first मैं has come, now second will come मैं घर. So in the second step, घर will come, and for the third here, the input will become घर. Then ja. So this will become ja. Then raha. So they will come one by one. They have not come instantly. So first I will cover the self-attention part of the decoder. So like the encoder, the decoder also does self-attention to find the contextual relationships between these words in the output. But at this step, for example, may, these words have not come. So it can use only this word. And the attention mechanism remains the same, that we have got WQ decoder, for example. We have got W key decoder, and we have got WV decoder. These are the three matrices which are there. But like I said, here at step 1, I should use only Q1, K1, and V1. Rest all words, it should be 0. There is no relationship. Is that okay? In the second step, when I go, I should be using only Q2, K2, V2, Q and Q1, K1, V1, Q2, V2, rest all should be 0. So as I keep on going forward, I keep on using Q1, K1, V1, Q2, K2, V2, Q3, K2, V3, and rest all 0. Is this understood?
Yes.
So unlike the encoder, where all the inputs were available to me at one go, here they are coming one by one. One, then it will come, then it will come, then it will come, then it will come, then it will come. So how do I use this? So what I'm doing, that at every step, at this step, I mask these. At this step, I masked these. At this step, I masked these. At this step, I masked them. So that's why this is known as masked self attention. And how do we do it? What do we do? I'll
So
just, yeah,
before steps are not masked, right? Like
yes, yes. Before that, okay,
okay.
information is available to me.
Only future timestamps are being
Yeah, for
masked.
example,
Okay.
I am at this step. Okay. Now this I don't know. मैं घर जा रहा
Yes, yes,
हूँ. I don't know. I don't know what is coming here. But I know
yes.
till now that these are the three words. So on this
Mm-hmm.
I can do self attention.
Yes, correct. Yeah.
Okay. So this I
Yes, yes.
mask, this I use, and that's why it is known as mask self
Masked.
attention. Okay.
Oh, okay. Got it.
And how do we do that? How we do that? We have got a matrix, something like. I'll just show you. Okay, this is the matrix. So in the first step, I use Q1 K1, and here I use minus infinity. So we know that, and we know after that we use the softmax function on this of Q1 K1.
Yes.
So softmax of in minus infinity is how much? Zero.
Yes, correct. Yeah.
So for all this, I don't consider. I make this value 0. So at one first step, I'm using only Q1, K1, then V1. Here I'm using only Q2, K2. Rest of all of them on the softmax, they will become 0. So this is how I do. So at every steps I know that at what step I am. So at that step, I will be using only that Q1, Q and K. That's okay?
Yes, okay. Got it.
Okay. Now, come to this. Okay. So this decoder part which was there, these were the inputs which have come in, and here I have done the masked attention, masked self attention, and by doing that same formula, S is equal to softmax of Q into K divided by root dk whole into V. I get the value of S. So here I get a value S output. Is that okay? Now this Z which is coming from the encoder, this dimension was 6 into 512. There are 6 words. Now here again I use 3 matrices WQ2, WK2. I should make WV2 here, WV2, WK2, and WQ2. So there are 3 weight matrices which comes to the decoder part. And now here for the cross attention, this is the cross attention part. Now for the cross attention part, I will use the output of this cross attention will be M, for example, and M will be equal to softmax of Q, and this Q will be Q is equal to WQ2 into S. K is equal to WK2 into the Z value which is coming for this vector Zi. V is equal to W V2 into Zi. Is this okay? And using this, I find M using the same formula softmax of Q into K divided by root dk whole into V. Is this okay? Suraj? Abir? Hello? Anyone?
Yes, sir. Yes, sir.
Is this clear? Anybody? Any doubt in this? So I'll just cover the architecture again. Okay? Coming to the architecture, I will rub this off and do this again. So see, in the decoder, this is the entire decoder part. Here decoder is giving input one by one in the regression. The output of first step becomes the input to the second step. Here we do the masked self-attention. And for the masked self-attention, we have got WQ decoder, W key decoder, WV decoder. By doing masking, because at every step, all the words semantics we don't know. So by doing the masking, we calculate S. And this Z which is coming, now again with this Z, we have got three weight matrices. WV, we can WV2, WK2 and this WQ2. Using the WQ2 and S, we find Q. Using the ZI and WK2, we find K. Using this, we find V. And putting in the same formula, we find M is equal to softmax of Q into K divided by root dk and into V. And this is the cross attention which we call. This is the cross attention part of the decoder. Is this clear? So at every step, when I am predicting the next, I am taking into the account of my previous state also, that what was the word. So for example, I am here at main, ghar, and I am predicting here for this. So here ghar has become the input. So I am taking the states in this S. So S captures both the semantic relationships between main and ghar. And from the encoder part, I am getting the Z. Q I calculated by using these matrices and S. V and K I use find from the encoder. So this M is having information from encoder also and from decoder also. Is that clear? Conceptually? Is that okay? Suraj? Abir? Surya? Shini sir? Am I audible?
You are audible. I'm fine. I've done LLM Lalit, anyway. I just joined just to as interest.
Okay.
But yeah,
Okay.
but this is the
Okay.
first part. I just put in the notes that you will get both assignment questions and quiz questions on these parts,
Yes.
including number of parameters, calculating attention scores for a toy thing. So
Yes.
these are to get them completely right.
Yes. Actually, sir, all of us, okay, we are transitioning to LLM. So I thought I will carry out a revision session for the DL week 11 and week 12. So at least those concepts are clear before we step into the LLM part. That was the idea. Okay, Abhi, can I proceed further? Anybody, any doubt till now? Give a thumbs up, okay, at least.
Yes, sir. Can you go to the slide?
Yeah, tell me.
Yes, sir. So the Z is the output from the decoder, right? The final output.
This is from the encoder.
Sorry, yeah, encoder. And
Yeah,
this is the decoder architecture.
this is the thing.
Okay. So, in the decoder, in each step, like what we are doing, we are like masking those like the sentences, right?
Yes.
Okay. So, like we have to. I'm not getting that thing. Like the input was मैं घर जा रहा हूँ, right?
No. See, input was in the encoder was I am, for example, I am not going home. This is the encoder part,
Mm-hmm.
and I am translating this to मैं घर नहीं जा रहा हूँ.
Okay.
Okay. So what happens? And this is a 1, 2, 3, 4, 5. This is 5, and this is 6. Okay. So from the input part, what we did self attention, and then we did feed forward, and we found the ZK value. So this ZK which is there, it is 1, 2, 3, 4, 5. So this is 5 into 512. This is the dimension. And what is the meaning this? that with these vectors, it is carrying the relationships also between these words. Okay, what are the semantic relationships and positional relationships also? So this like a relationship I have got in Z. Okay.
Okay.
Now at every step now, when I do in the decoder, so how the decoder works, that I first feed go and I find an output using the softmax.
Mm.
Okay, and which should become ma. This ma becomes the input at the second step.
Okay.
Okay, then it will give me ghar. So ghar will become next step. Ghar ke baad mein will come nahi. Nahi will become second step. So what the mask, what does it mean in the self attention of the decoder? It tries to find the semantic relationships and the positional relationships between these sentences. But unlike the decode in encoder, in the decoder, I don't have these inputs at one go. They are coming one by one.
Yeah.
Okay, so what do I do? So I have to mask them. Okay, so at first step, what do I do? At first step, I use only Q1, K2, and rest all I do minus infinity, because when what I do, I find like a softmax of Q1, K2. So for rest all, it will become zero. Softmax of infinity is zero. Okay, because e to power minus infinity is zero. At second step, I use Q1, K1, Q2, K2, rest all infinity. So at this step, I use only may. At this step, I use both the words may and ghar. At this step, I use all the three words may, ghar, nahi. Okay. Here I use मैं घर नहीं जा. So at every step I don't have all the words. I have got only one by one. And how I am achieving this? I am achieving by this masking and making a matrix like this, which I had shown you. This is the step 1, 2, 3, 4, 5, 6. Here I will use only Q1, K1. This I do minus infinity, minus infinity, minus infinity. Here I will use Q1, K1, Q2, K2, rest all infinity. Okay. Q1, K1, Q2, K2, Q3, K3, rest all infinity. So this gradually I keep on going. And the output of this multiplication which is there. So if you remember, from the
Sir,
encoder.
one thing
Yeah,
that,
yes,
we first of all, when we are putting that मैं घर जा रहा हूँ, so we are encoding that मैं थे, right? And then we are giving that encoded part to the decoder architecture, right?
yes.
Like that encoded part is being multiplied with Q. You are saying that?
No, 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 no. So again, I will talk. Okay. So I will make some things. Input is I am not going home. Okay. And when we do word embedding plus position embedding, my input becomes 5 into 512 size. Is that okay?
Yeah.
Now, I do self attention on this by using Q, V, and K, using WQ, WV, WK, and final output. And this output which is there, which I say S is equal to softmax of Q into K to DK into V. This S I feed it to forward fully connected layer and I get Z. The size is 500 to 500. This is clear. This is the encoder part. Okay. Now when I come to, so this is encoder, full encoder, and it has given me this Z. Size is 5 into 512. Now I come to decoder. This is the entire decoder. So first step of the entire decoder is what I do. I give him go.
Yeah.
Okay. So first input is go. Okay, and I will not covering this self attention part here presently. This is the cross attention, and in the final output which is there, I should get man here.
Yeah. Next on input.
Okay, so in the decoder also now this man will become next input to here.
Right.
Okay, now see this part is the self attention of decoder. But unlike encoder, where I am not going home, I had all the words at one go. Here I don't know which is the word is coming next. So for the self attention here, I can use only my. So it means I will use only here. I have got weight matrices W Q W K W V for decoder, and here I will get so WQ when I multiply WQ, I get Q decoder is equal to WQ into this entire thing, which I don't even the length also. So I will get okay, some Q vector, Q1, Q2, Q3, Q4, Q5, all this.
So WQ is multiplied by what? Encoded words, is it?
No, it is not getting multiplied by this. Please, okay, so here these W's are different. Here these W's are different. Okay.
Oh, okay, okay. It's different set of vectors.
Yes. These are different set of matrices.
Yeah, matrices.
WQ, WK, WV are their matrices, and these are different, and here they are different. Okay. Using this WQ, WK, and WV with masked attention, with masking, we get an output here S. Okay. And this W, this is different. This WV, WK, WQ, let's call them 2. Okay. Now with this W2Q, you use this S. Okay. And with the ZI, you use W2K to get K. It will give you K. This will give you Q. This will give you V. And again, using the formula of that softmax into dot V, here you get M. Okay. So this M which is there, it is also vector. It will have M1, M2, M3, M4. It is like this. And now you, like the encoder, you pass it through forward, okay, forward feed network to have the non-linear transformation. And then you do a linear transformation. Why do you do the linear transformation? Because these embeddings and the vector size which you have got, it might be of the size 512, where when I'm doing the translation, their embedding size might be 1024. So I have to convert that size into 1024.
Right.
So for that, I do linear transformation. And finally, I apply the softmax. Okay. Now in this softmax, when I do argmax, I get the output. So here I will get now ghar. So for the next step, I will come to ghar. And when I do self-attention, now may and ghar will be different. Is that okay?
Okay. Okay.
Okay. So this is how your decoder part. So decoder has got 4 main concepts which you should understand. One is the masked attention, masked self-attention. Here you have got W, Q, W, K, W, V. They are different. Okay. Then you have got crossed self-attention. So again here you have got W, Q, W, K, W, V, which are different. You can call two. Okay. Then you do feed forward NN for non-linear transformation. Then you feed it to linear to match with the target, to match with target language embedding. Okay, and then finally you do softmax for classification. Is that okay? Is that okay, Aditya? Abir? Or Shini sir, have I missed out anything?
It's okay, sir.
Okay. Okay.
Yeah, not anything that I
So
could think of.
yeah, thank you, sir. Thank you. So I will go through once again. So what we have covered today, we started with self attention. What is the first of all, we started with attention. What is the meaning of attention? And we took an example of simple encoder and decoder and how we were doing that. And then we, with that concept, we came to transformer. And in transformer, we have got encoder and we have got decoder. Okay. Then we came to encoder. In encoder, the difference between the encoder decoder encoder and transformer encoder is that input embeddings, and what is the input embeddings are word embedding plus positioning embedding. Then we do self attention or here. Self attention, it can be single head, it can be two head, or generally it is 8 head. Then in case of multi-head, what we do concatenation. Then after concatenation, we feed it to feed forward neural network. And why do we do that? We do that for the non-linear transformation. Now, output of this is Z, and this output is having basically the, you can say, vectorization of the inputs along with the semantic and positional relationships of the inputs. So this Z becomes the, now we come to decoder. So here we have got Z from encoder. Before this using Z, so remember in the encoder decoder, this was the encoder, this was the decoder, and directly we used to use this information for the decoder at different steps using context vector. But in transformer, what do? We do the self attention on the decoder also. Like as I'm doing the translation or I'm having the outputs, I try to find the semantic and positional relationships between the words which already I have found. So in the decoder, the basic parts we call decoder. So we do self attention first, and it is masked. And again, it has got WQ, WK, WV. Then after the self attention, I do cross attention. So again for the cross attention, I got WQ, WK, WV. Once I have done the cross attention, I pass it to the feed forward network. After the feed forward, I pass it to the linear one. And after the linear one, I pass it to the softmax to get the output. And here I will have parameters. Here I will have parameters. Okay. Here I have got parameters. This I have got parameters. Here I got. And similarly, in the encoder, I have got the parameters in the W's and the feed forward network. So once you are given a question, then you can easily make out that what will be the parameter here, what will be the size of WQ. So in encoder, I have got WQ, WK, WV. Then I have got feed forward neural network. It also has got two layers. So two W1, W2. So this will be the my matrices. So these are the total number of parameters in encoder. When I come to decoder, I have got self attention WQ, WK, WV. Then I have got cross attention WQ, WK, WV, which are different. Then I got feed forward neural network. Here also I'll have two matrices W1, W2 dash. And then I will have linear. So for the linear also I'll have some uh, vector, or I'll have a matrix, sorry, matrix. It will have some size. So these are the parameters in the decoder, and these are the parameters which I covered earlier in the encoder. And once you go through that, you can easily find the number of parameters. With this, gentlemen, I have finished. Okay, in case anybody has got any doubt, you can ask. So I have covered basically attention slightly fast, and thereafter I covered the encoder and decoder part in detail. In case any question, you can pipe up and ask me, please.